Okay, let's stay on the topic of computer-aided engineering. I would like to give you an overview about the status of GPU acceleration for CAE codes. So what is the outline? First, I would like to give a general overview about GPU efforts in the CAE market. Then I will go to some CSM, to some computational structural mechanics codes like ANSYS Mechanical, SIMUILA, Abaqus Standard, Nastran from NSC and Mark from MSC. Going to computational fluid dynamics codes like ANSYS Fluent and some OpenFOAM plugins from FluidDyna and PARALUTIon, and at the end also to one code in the computational electromagnetics from CST, a German company with a CST studio suite. So in general, status about the ISVs and GPU computing, more or less every primary ISV has a product which is available on GPUs or is evaluating GPUs. So the four largest ISVs, ANSYS, SIMUILA, MSC and also Altair, has products which supports GPUs. The most successful applications, so 4 out of 5 ISV applications are available on GPUs today, which is ANSYS Fluent, ANSYS Mechanical, SIMUILA, Abaqus Standard, and also MSC Nastran. For LS-DYNA, at the moment, it's only the implicit solver implemented on GPU. And there are also several other ISVs which have applications ported to the GPU. So very successful applications like AccuSolve and OptiStruct from Altair, or also NX Nastran from Siemens, Permas from Intes, or Fire from AVL, and Moldflow Autodesk, and also the solver from CDH, AMLS, and Fast FRS. There are a lot of new startup companies which were founded with a GPU as a primary competitive strategy, like Prometec, FluidDyna, Vratis, Impetus, TurboStream. A lot more are on the horizon, and one of the most successful open source codes in the CAE markets, OpenFOAM CFD software. There are a lot of solvers implemented on GPUs, commercial options from FluidDyna and Vratis, but also open source options from Kaflame, Simscape, or OFGPU, or from RAS, from a Russian company. So in CAE, you often have the domain decomposition, so a model will be separated in several domains which were distributed to the several cluster nodes. Nothing will change with this model when GPUs come into the place, so the GPUs support the computational work on the different nodes. If you categorize the software, on one side you have structured and unstructured grids, and you have explicit and implicit solvers. And so we prioritized a little bit the efforts. So of course, when we are looking to implicit and unstructured codes, we have very often direct solvers. And you have in this direct solvers, or in this applications, a hotspot which consumes normally around 70 or 80% of the total compute time. So you can implement, of course, these kind of solvers very easy to the GPU and get a very good speed up. So This was our #1 priority together with the ISVs in order to implement, for instance, ANSYS Mechanical or Abaqus Standard, Nastran Mark, LS Dyna Implicit Radios, NX Nastran, and Autodesk Mechanical. On the other side, you have here iterative solvers, so the hotspot is not such big, but you have around 50% maybe of a total runtime will be spent in the solver. And here the strategy is to use CUDA to implement these kind of solvers and also to use GPU accelerated libraries. So examples for this approach are ANSYS Mechanical 2, Radius, Accusolve from Altair, and also Moldflow. Then we are coming to more CFD-based codes like ANSYS Fluent or OpenFOAM, or also CDApp-DAPCO with StarCCM+, and also codes from Easy and SIMUILA, Abaqus CFD. So this is more or less the same like the iterative solver, the same approach. A little bit more complex are the explicit codes because you typically don't have a solver with a hotspot, so you have stencil codes, and the strategy for this kind of GPU approaches is to use OpenACC for these flat profiles. So LS Dyna, the explicit or Radios explicit part, or also PEM crash. So these are more or less the crash codes which are also heavily used in the automotive industry, for instance. So coming to the computational structural mechanics, the first code is ANSYS Mechanical. So we have a long collaboration with ANSYS. The first GPU-based release for ANSYS Mechanical was introduced into the market in December 2010 with the version 13. Over the time with the versions we optimized the performance, and we added new features like the multi-node support and the distributed support, multi-GPU support, and also we introduced the new GPUs supports, for instance the Kepler support, and the latest version which is currently available is the ANSYS 15.0 version, which got a lot of tunings for Kepler. Coming to some benchmarks, normally we are comparing a socket, a CPU socket, to a GPU, but in case of CAE, we often have licenses which are based on core, on CPU cores, also on GPUs. I will cover the license topic a little bit later, so that we are comparing here in CAE very often other granulators like cores plus GPU. In this case here you see ANSYS mechanical jobs per day. With 2 CPU cores, we got 93 jobs per day. With an additional Tesla K20, we get 324 GPUs jobs per day. So it's an increase by a factor of 3.5. And also here, with the next model, we see comparison between 8 cores and 7, in this case 7 cores plus a Tesla K20, which consumes the same amount of licenses from the ISV, but you get a factor of more than 2 more ANSYS jobs per day. So this is a standard ANSYS benchmark with 2.1 million cells here, and I will cover some other benchmarks with other applications as well. So considerations for ANSYS mechanical on GPUs. Of course, problems with high solver workloads benefit the most from GPU. So these are characterized by a high degree of freedom and high factorization requirements. Models with 500K degrees of freedom show very good speedups in our benchmarks, and you get a better performance when run on the DMT mode instead of the SMP mode. For the different solvers, the memory, both on the system side and also on the GPU side, play an important role. For instance, for the sparse solver, if the model exceeds 5 million degrees of freedom, then you have to add another GPU with 5 or 6 gigabyte of memory, so the K20 or the K20X, or you should use a GPU with larger memory. In this case, here the Tesla K40, for instance, with a 12 gigabyte of memory. For the PCG, GCG solver, so you should turn off the memory saving option, and also the models with lower level of difficulty values, the so-called left diff, are better suited for GPUs. Next code in this area is SIMUILA Abaqus standard. Also here, a very long collaboration with SIMUILA in order to implement the solvers on the GPU. The first version came out in June. The first version with GPU support came out in June 2011. Direct sparse solver was accelerated on the GPU. Only a single GPU was supported at this time, and at this time the Fermi GPUs were available. So for instance the Tesla 20 series or also the Quattro 6000. So in version 6.12 in June 2012, multi-GPU support and multi-node support were added to the version, and also at this time the Kepler came out, and SIMUILA provided a Kepler performance optimization fix, which was fully integrated in the version 6.13, the current version. And also in 6.11 and 6.12, only symmetric sparse solver were supported, and in Abaqus 6.13, both unsymmetric and symmetric sparse solvers are supported. So officially supported also the new Kepler GPUs, K20, K20X, K30. Also here, some benchmarks which were done by Rolls-Royce. 4.71 million degrees of freedom, so computational load is around 77 teraflops. Direct sparse solver, you see here the runtime, the elapsed time for socket, so with 8 cores plus 1 GPUs gives you a performance improvement by a factor of 2.42, and additional GPU also gives you additional speed up. So with 16 cores, so with one node with 2 sockets, you see here it's maybe 21,000 to 12,000 or 13,000 around, so nearly a factor of 2 with a GPU version, but with 16 cores and 2 GPUs you get another factor of 2, more than a factor of 2. Another run done by Royce is on a cluster. So you have 2 servers here, 24 cores, and with 2 GPUs per server, in total 4 GPUs, you get a run performance improvement by a factor of 2.2, and also on 4 servers you have nearly a factor of 2 with this model in the cluster. I introduced in the morning talk also the K40, which has this boost clock mode, and here's a comparison of different models with different degrees of freedom on 8 cores on a socket on a CPU, and you see here with the Tesla K20 you get a speed up of 1.5 to 2.5 dependent on the different models. With a K40 you get an additional speed up here ranging from 1.7 to 2.9 against single socket CPU runs, and on 2 CPUs more or less the same picture. So 1.95 to 4.1. So the green is a 4.7 million degrees of freedom. Benefits most of the GPU, and you also see here the same picture like on the comparison on 1 GPU with the 8-core socket. This shows you the number, especially the speedups and also the tokens you need from the license server for running the model, and you know that the licenses are very expensive, so in the total cost of ownership, license costs are very important. On 8 cores, Abaqus again, you need 12 tokens here, and you have elapsed time in hours of around 18 hours, 8 cores plus 1 GPU, also 12 tokens, and you get a speed up of 2.2. So with 16 cores and 16 tokens, you have a speed up of 1.7 against the 8-core version. So this means you are faster with 8 cores and 1 GPU with a lower amount of tokens compared to the 16-core version. So, and you can go over the different configurations here, and you will see that you get a lot of improvements with the GPUs in terms of runtime, but also better efficiency in terms of using GPU tokens or license tokens in this case. So regarding licensing, it's a complex formula for Abaqus, and you see here when you are using 1 core and you need 5 tokens with an additional GPU, you need 6 tokens, and you can go through this table here, and for instance for this run here with 8 cores and 1 GPU, you need the same amount of tokens in order to run the application. So the licensing is very good for GPUs. So this is true for most of the CAE codes, or for some of them at least. Normally a license which you need for a CPU core, you also need the same license token to use a GPU. Another aspect we discussed yesterday also on the exascale panel is the power consumption. We did some measurements for one of our customers. This was with version 6.12 in a node, 2.15 million degrees of freedom. And you see here the total estimated power consumption. So with 8 cores, it's a long runtime here, and you need 2.14 kilowatt hours. With 16 cores, you need half of them, or around half of them, with 1.44 kilowatt hours. With 8 cores plus 1 GPU, this is this run here, 1.25 kilowatt hours, and with 16 cores plus 2 GPUs, it's the fastest, and you need only 1.07 kilowatt hours. So this comes into the play also when you are talking about total cost of ownership. So licensing costs, runtime, and power consumption are very important for the engineers. Next code in computational structural mechanics is MSC Nastran. So direct equation solver is GPU accelerated, but not all of the so-called solutions in Nastran profit from GPU. So very high impact have the solution 101 and solution 108. Medium impact has a solution 103, and at the moment only a small impact has solution 1.11 and solution 400. Support of multi-GPU is in Linux and in Windows, and with DMP, distributed modeling, larger than one, multiple fronts are factorized concurrently on multiple GPUs, so multi-GPUs supported, and one GPU will be used per matrix domain. So all the latest GPUs are supported, which means Fermi-based GPUs and also Kepler-based GPUs, including the Quattro 6000 GPUs, and you need CUDA 5.0 or later. So here are some benchmarks with different solutions, solution 103 and solution 104. So you see here a serial run, the blue one. The red one is a run on 4 cores, and the green one is a run on 4 cores plus 1 GPUs. So you get a speed up of 6 when you compare the serial run with a 4-core run plus GPUs, or more or less you double the speed up when you compare 4 cores and the 4-core run plus 1 GPU. That's Tesla K20X GPU in this case. So similar picture here with another solution, 103. Here you see a coupled structural acoustic simulation with solution 108, and also a serial run. This is the elapsed time here, and you see here the different speed ups. 1 core plus 1 GPU gives you an improvement by a factor of nearly 5, and you see here a factor of 11 when you compare the serial run with the 8-core plus 2 GPUs, or nearly double the speed up when you compare 8 cores plus the additional 2 GPUs. Okay, last in the structural mechanics is MSC Mark. 2.5 million elements for this input set and 7 million degrees of freedom. And you also see here is more or less the same picture. So matrix factorization time on this side. The blue one is a CPU Speedup, and you see here the GPU Speedup with different configuration in this case. And the red curve, the red line, is the total elapsed time. CFD, ANSYS Fluent. I mentioned the long collaboration. For Fluent, the first GPU accelerated version was a better version for the radiation heat transfer in version 14.0. In 14.5, this was a fully supported feature, and also this was the first version which introduced the AMG solver, the so-called AMGX solver, which was developed by NVIDIA and integrated into the ANSYS Fluent. It was integrated as a beta version at this time, and supported single GPUs. Meanwhile, with the newest version, the multi-GPU AMGX solver is fully supported, and there were a lot of Kepler tunings integrated into this 15.0 version. So, how to enable the NVIDIA GPUs in ANSYS Fluent? You can do it on the runtime here with a Fluent call, or you can also use in Windows Fluent Launcher here. So this means 3D dimension, double precision, and you can give the arguments total number of Fluent processors and the number of GPUs you want to use per host. And there are some requirements. So for run, the same number of solver processors on each machine, and the number of processors should be an integer multiple of GPUs, which means for a single node configuration, you can run 16 core or 16 process job with one GPU. You can also run this with 2 GPUs, so 8 MPI processors sharing one GPU. You cannot run 16 processors with 3 GPUs, so you have to let one core free, so that you can use 5 MPI processors per GPU. Similar here to the multi-node configuration, so this does not work when you want to use 2 GPUs with one node and one GPU only with the other node, so you have to be the same number of GPUs on every node. Some considerations for ANSYS Fluent on GPUs. So the AMG solver will be accelerated by GPUs. Fine meshes and low dissipation problems have often very high AMG solver times, computational load. Coupled solution scheme spends 65% on average in AMG. In many cases, pressure-based coupled solver offers faster convergence compared to the so-called segregated server, but this is of course problem dependent. So the system metrics must fit into the GPU memory. So each 1 million cells need about 4 GB of GPU memory. High memory GPUs such as Tesla K40 or Quadro K6000 are better suited because they have this 12 GB memory, GDDR5 memory. Better performance with use of lower CPU count, so a ratio of 4 CPU cores to 1 GPU is recommended, but it's problem dependent very often. So which solution fits with ANSYS Fluent on the GPU? So is it single phase and flow dominant? Yes. Which solver will be used? I talked about the pressure-based coupled solver or the segregated solver. So the pressure-based coupled solver fits best for GPUs. So if you are using segregated solver, then you can often consider if you are switching to a pressure-based coupled solver for better performance and for using GPUs in order to get this additional speed up. Some performance numbers also here. Better speed ups with larger problem sizes as expected. So we have here a 14 million cells job and here a 111 million cells job. And we see here a factor of 1.4 for a speed up on 3 nodes here. A node has 12 cores and 4 K40 GPUs per node, and with a larger problem size here you get a higher speed up with a GPU based runs. Here's another model where you can see the AMG Salver time. So you get a speed up of nearly 6 with a CPU socket, 8 cores, plus 2 Tesla K40. The solution time gets at the end a factor of 2.5x speed up. Here are some studies on productivity gains, number of jobs per day again. So you have 16 jobs per day on 4 nodes with 2 GPU each, so a total on 64 cores. And you have also 16 jobs per day, but you only need 2 nodes with dual socket CPU and 4 GPUs in each. So you save the costs for two nodes, and you have to add, in this case, additional GPUs, but you save a lot of network costs and so on. So in total, 56% increase in overall productivity for 25% increase in cost. I mentioned licensing is very important. Also for ANSYS Fluent, you need 1 HPC token to enable a GPU, similar to a token for 1 CPU core. CFD OpenFOAM. So we are providing technical support for GPU solver developments from different companies, Fluidina, for instance, or the Russian Academy of Science is developing OpenFOAM solver on GPUs. Also here the cufflink developments by David Combest. We invest in strategic alliances with OpenFOAM developers, with ESI and the Open CFD Foundation, for instance, or with the OpenFOAM extended community. And we are working together with a lot of OEMs and customers and developers in order to perform performance studies and customer evaluations. Here's an example, some slides from Fluidina about their Culises library, which they presented last week at GTC. So Culises is a library, state-of-the-art solver library for the solution of linear systems. It's multi-GPU supported and also multi-node capable. provides a lot of Kirchhoff subspace methods and preconditioning options, standalone multi-grid methods, and so this the linear solver will be implemented by the Culises library, which is using the GPUs. And so there are a lot of advantages for this approach. It's fully available on existing flow models, but it has also some disadvantages. For instance, in case that solution of linear system is not dominant, then the application speedup can be very limited. Therefore, Fluidina started another project, the Aero Fluid X, where they also bring or implement the discretization phase to the GPU, and so they couple this directly on the GPU with the Culises library, and this gives you much better performance. And this is also available as a plug-in for OpenFOAM, so you can use this with an OpenFOAM framework. Here are some benchmarks they did with their new code here on GPU 8 cores, the blue one with OpenFOAM, and with OpenFOAM plus Culises, where only the linear solver is running on the system, and with a new software where also the discretization is running on the GPU. So you get here a better speed up. So it's a lot of work has to be performed because you need to optimize this. So it's more or less an unoptimized version at the moment. So they are working on the optimization. Another C++ library to perform sparse iterative solvers is the PARALUTION library by the company PARALUTION. Also a lot of solvers are implemented, many core CPU and GPU support. PARALUTION library is open source, released under GPL license. And here are some early benchmarks for the OpenFOAM plugin, which were also presented last week at GTC. So you see here a speed up, or you're running OpenFOAM on a single core, then OpenFOAM on 4 cores, the PARALUTION CPU version, and at the end the PARALUTION GPU based version, and you get around a factor of 2 with the GPUs added in these cases. So OpenFOAM plugin will be released very soon in summer time frame, as the developers mentioned. Last code I want to show some benchmarks is the coming from the computational electromagnetics. That's CST Studio Suite. So CST is a German-based company, one of the largest suppliers of 3D electromagnetic simulation software. They are located in Darmstadt. They have a lot of solvers, and currently 3 solvers are supported on GPUs. So these are at least one of the most important solvers is also implemented on GPUs. So you see here some performance numbers, which compares the K20 versus the Tesla K40 GPU. So K40 has a doubled memory and also gives you a PCI Express 3 instead of PCI Express 2 with a K20, and you see here with an increasing number of mesh cells, you get a higher speed up with a K40 instead of the K20, so 1.37 or something like this, with in this case the largest model here. Also, they improved the version 2014, and they now have a better load balancing between the CPU and the GPU. That's often also a problem which has to be solved, because if you perform all the computation on the GPU and the CPU is doing nothing, then it's not good. So you have to load balance the work between the CPU and the GPU. So with this, you see here over the number of GPUs here per node, up to 4 GPUs per node, in this case Tesla K40, you see the improvement here from one version 2013 to the other version 2014. Okay, and here you see the speedups for the solver loops compared to a dual socket Ivy. What is this? It's a Sandy Bridge server in this case. So with the blue curve, you add 2 GPUs, K20 per node, and you get a speed up here with 4 nodes by a factor of 15, nearly 16, and with 4 GPUs per node and 4 nodes, you get a speed up of a little bit more than 20 in this case. In conclusion, so GPUs are providing significant performance acceleration for solver, especially for large jobs, so for large input sets, which leads to shorter product engineering cycles. So faster time to market is a keyword, a buzzword in this case, which improves the product quality and the product cycles. Cut down energy consumption in the CAE process is meanwhile also a very important factor. Better total cost of ownership. So GPUs for second level parallelism preserves costly MPI investment, so you need fewer nodes and so on. GPU acceleration contributes to the growth in emerging CAE spaces. So we see a lot of new ISV developments in, for instance, particle-based CFD. Lattice Boltzmann is running very well on GPUs, SPH methods, etc. I provided an overview about CEM, electromagnetics application with the CST. So it's we see a growth in this area of magnetics applications. And at the end, so with GPUs, simulations considered intractable are now possible. For instance, large eddy simulation with high degree of arithmetic intensity, and also something like parameter optimization with a highly increased number of jobs are now possible. With it, I will end my talk, and I'm open for questions. Thank you.
Any questions for us? Okay.
The licensing model that you were looking at there, that seemed very generous to GPUs. Is that across the board for ISVs, or just something else?
Yeah, at the moment, it's a general license model for instance, SIMUILA or for ANSYS, so for the largest one. The smaller one have often different models, so they are not licensing in terms of CPU cores or GPUs. They are often licensing complete nodes, independent if you run on one core or on 2 sockets or system with GPUs. So, but for the largest ISV applications like the one from ANSYS or from SIMUILA, that's true over all the applications.
They don't typically count the number of cores in the GPU at the size of the GPU.
No difference.
What's the run?
I believe ISVs are meanwhile under heavy pressure to follow the larger input sets, and so the demand is increasing in the industry, in manufacturing or in other areas, and they have to provide good solutions. And so with GPUs, with MPI, it often does not scale very well over a large number of nodes, so GPUs give them additional benefit in order to run new large eddy simulations or parameter optimization runs and so on. So it does not decrease the number of licenses. At the end, it will increase the number of licenses industry will use.
But it does seem like it tips the scale pretty well in favor of GPUs to do that. It seems like it encourages.
Yeah, that's right. So the ISVs also invested a lot into the GPU port, and so of course they will get some benefit from this effort.
Any others?
Okay, let's go to the boat.